Hello guys, with me again. This is Instrumentation SKMM SEMM 3242. Now we are looking at lecture 4, which is on dynamic characteristic of system of instrumentation. Alright, let me get a slide up for you. Okay, here you go. This is lecture 4 on dynamic characteristic. This is basically the last lecture for the first part, for the introductory, for the theoretical, and for the performance calculation part. All right. So previously we have seen how we describe system of instrumentation or components of instrumentations in terms of its characteristic, which very much divided into three. The first one is operational. All right, just a little recap. And then the second one is static. Um, and now we are looking at the last part, which is dynamic. Okay, as just to remind you, the operational characteristic is the characteristic of sensors or actuators or in a system of instrumentations when they are not plugged in into the system. It's basically you first refer to this thing on the data sheets, on the online catalogs, as I mentioned, right before you buy that particular sensor, right before you have those things in your hand, basically. All right. So that's for operational, but for static, now you have the equipment, now you have the sensors in your hand, you plug into the system, into your prototype, into your instrumentation devices, you power on. This is where you observe the static characteristics. There is no changes in the environment whatsoever, so this is where you observe it. And then the last part is you have the dynamic characteristic, is when when your sensors or devices are very much plugged in. You turn on the power and you start observing the changes around it. Okay, this is characterized by dynamic behavior of the system. Okay, also it says here that static transfer function is basically how output related to the input when the input is constant. Okay, so when the input start changing, when the time start changing, and the input and output respond to the change, we have to also describe it using the dynamic transfer function. Okay, so basically this is a response of a sensor. You have CT in the input and BT in the output. All right, and the response basically show how the input and output change over the step using a step function at the zero in the axis, meaning that the previous state of the current of the sensor at the CI level, and suddenly you switch off the system, or suddenly you detect something, it change the magnitude, the amplitude to CF basically. So this is basically the change that we are describing. You won't see this kind of response in the operational or static characteristics, but for dynamic, this is the response that we are looking at. Changes in the system behavior. All right. So as I mentioned, to describe the characteristic of system of instrumentation in the dynamic mode, we are working with differential equation. In this case, you have all these variable AY, you have B and you have U. is described by the input output. A, B are very much constant in this equation. Okay, you can basically A works with Y output. Okay, A is a constant in the output and B is a constant in the input. So this is how the input and the output is very much related. You can see the same representation by this differential equation, ODE, using a transfer function of accelerometer. So you can describe the whole situation in the picture using the equation down below. So you have the first term, the second term here until t2x, d2x, dt2. And then to the right side also the same, which is this is how the system relates between the input and the output in the system of accelerometer. Okay, okay, so describing the changes, representation using differential equation, you have to look at in this case three different scenario. The first one is zeroth order response, the second one is the first order, and the third one is second order response. So equipment designed to perform different function, they act differently, they respond differently. So this is some kind of classification of the dynamic behavior of the system. Okay, so the first one is the zeroth order. Basically there is no, if you this one, if very much derived from the equation here and here and here. If you remove the t function, because this is zeroth order, so we are not looking at any changes in terms of time. So we remove all the t. If you remove all the t, basically you just have the first term here. If you remove the t terms, you have only a naught y equal to b naught u. So this is what you have here, and input over output, basically, or output over input, you have k. It's a constant. Okay, this is described by the zeroth order. So basically, the whole situation, the whole period of system is up. The relation between input and output is just this. Okay, so it's a linear relation. Okay, for example, potentiometer, once you turn the potentiometer knob to some point, the reading will stay like that forever until you turn or twist again. Or in this situation, no matter when or at what time you do the turning, the reading are all still the same. Okay, it doesn't taking the influence. It doesn't take the influence of time into the consideration of the value. Okay. If we look at the second classification, is the first order. In the first order, you are including the a1 dy dt into the term. Okay. If you remove the a1 dy dt, you are looking at the zeroth order. If you add in a1 dy dt, you are working with a first order system. So in this case, you have some time influence into the system. In this case, you have a time constant. When putting the whole equation into a simplified form, we have output over input. You have k over 1 plus td. T is time constant, basically, in this case. So for this particular scenario, you have t, the big capital T, represent the time taken from the output to reach 63% of the final value, and it reaches final value approximately 99%, around 5t. So t is a general constant in this case. T is not actually directly related to time, but t is a constant in which is used to describe that if the system reaches t, capital T, meaning that the system is reaching 63% of its final value, and the final value is represented by 5t. This is constant. You have to just take it. All right. Don't ask me why it is 5 or 3, because it is set in this manner in this first order system. Okay. So if you look at this table, you have TYD and percent basically. This is the response of the first order system. If you look at the T is 63%, 2T is 86%, 3T 95, 4T 98%, 5T is 99. If you go further, you are still looking at 99%. So 5T meaning that the system complete its cycle. First T, 1T or one or capital T, meaning that the system is completing only at 63% of its cycle. 2T 86%, 3T 95%, 4T 98%, and so on. If the system reaches 5T, we say that the system is completing its cycle. Okay, for example, this is the graph for the first order system. Okay, so to see this thing a bit on the clearer picture, basically, let me see what we have waiting for us. Okay, to see this thing in the much more clearer picture, please take the example of a kettle. Okay, the boiler. Okay, cari air. All right. So when you fill up the water into the kettle, you connect this thing to the power source. You switch the power on. Basically, you won't be getting the water boil up at 100 degrees straight away. It will take certain time. Maybe it's different from manufacturer to manufacturer, but different from power rating and all that. But it will certainly take the shape, meaning that it will start somewhere, it will go up gradually, and it will reach some steady state somewhere, and they will stop. Okay, so those kind of system basically follow the working model of this graph. Basically, they will reach 5T in certain time period, for example. But the whole working principle or working cycle of first order system, taking the example of a water kettle, the boiler, this is the graph that the system is following, and you can always describe the behavior of that jug kettle using this load line, using this graph model. Okay, it's just that different manufacturer, different jug kettle, different boiler, they reach 5T in different time according to the design, according to the power rating and all that. Okay, but we can use this term T and 5T in all of the cases. Okay, so this is basically the general equation as a function of time for that particular case, which is in this case the first order system. So you have yt equal to yi plus yf minus yi, and you have exponential term. If you look at this graph, it is actually a negative exponential. All right, so you have exponential function in this case. So you can basically use this equation to describe or to predict the behavior of a jug kettle boiling the water to 100 degree of temperature. So meaning that in this case here, the 5T is equal to 100 degree of temperature, and as I mentioned, different kettle reaches 5T in different time. Okay, so this is the response basically. You can always look at this example. A sensor measure temperature linearly with a static function of 33 millivolt per degree Celsius has a 1.5 S time constant. So T in this case is 1.5. Find the output of 0.5 after the input changes from 20 to 41 degree. Find the error in temperature of this represents. All right. So for this, if you look at things that works using the first order system, you have to always go back to this formula, and you have to memorize this formula. Okay. So information is very much given. Okay, static function, so you have to convert the information to the right unit so that you can start working on it. Okay, you have yi, you have yt, and you can start putting everything in the value. As I mentioned before in the question, they say t is equal to 1.5. Now we are looking at 0.75, 1.5 seconds. This is capital T. Okay, so they say find the output 0.75 second after the input change. Okay, so you can put minus 0.75 over 1.5 exponentials. Then you have y output at 0.75 second after the system start is actually in that voltage. See, so basically using the load line, using the same first order equation, you can basically predict what is the voltage output at any particular time when the first system orders when the first order system is working. So it's good that we can predict the behavior of all engineering equipments. All right, so for the first order system, you are using this equation, and basically when you know the time constant of any given devices, basically you know what happened at any moment to the equipment, basically. All right, so you can basically continue, on to what the question want, basically. All right, so this is the very last part, the dynamic response of the second order instrument. In this case, you have the zero order A not Y. For the first order, you add in A1 dy dt. And for the second order, you have A2 d2y dt squared, basically. All right. So you are adding more terms to go on the more order. Okay. I will just go through. Okay, this is the most important part. If you can find equipment that works in this way, basically the equipment is classified as a second order system. Okay, so the best example to work with here is it's like taking the elevator. You start at certain level, you stop at certain level, but actually the control system, it doesn't work in it doesn't always work in the manner where you press level 5, it will stop at level 5. Okay, this is what you observe now because the system is very, very sophisticated. But previously, in order to reach level 5, the control system like the sensors, the motors, basically they will basically overshoot and try to readjust to the system so that the level is correct, basically. If you notice in some elevators when the function is a little bit not optimized, you will see that the lift is basically stopping. You have some gap between the lift and the floor level, and the system will make correction. Okay, basically, for example, if you want to go up to a certain level, you normally notice that they will basically stop at the right level, and you can go out straight away. But in some situation, you will observe there are some overshoot gap, and the lift is adjusting, basically. So this is basically what they are doing. Before this, when the system of instrumentation is not that sophisticated, the gap is big, and the lift is basically taking time to stabilize to the level, and then they stop, and the elevator door opens. But currently the system is responding very fast and very precise. You won't notice this kind of level adjustment job, because everything, first it is precise, second it is fast, so the adjustment will take like in milliseconds. So you won't notice that this graph or this process is taking place in your elevator system, for example. This is one example. You can find many other examples, and this is how you describe the second order system. Second order system basically follows mass spring and damper concept. You may have seen this in control subject, and these are the they call that equation for the second order system. Okay, not going to the detail. We normally we don't ask, we don't have exam question in this section. Okay, so the same thing which you can see from control subject. For the second order system, you have under dam, you have over dam and dam system. You can control the operation of the lift by controlling this kind of response, basically. Okay, so I think that's all for lecture 4. I'll see you again in the next lecture. Goodbye.